right. Hi, Verge. Hi, everybody else. Welcome to week 2 of AP Live and our
Hi,
new
everybody else. Hi, Mark.
generic slide to begin the lesson. So 7.4 is what you're here for today. I'm Mark Crowley. I'm from Ryan High School in Denton, Texas, and I will be kind of leading today's session as much as one of us leads.
Hi, everybody. I'm Verge Cornelius. I'm probably guilty for having my YouTube open. I don't know why that was open. And I'm at Lafayette High School in Oxford, Mississippi. And welcome to our 4th session here, AP Live, AB Calculus. We got some examples for you.
All right. So what are we doing this week? This is an overview of the coming weeks and this week. We're going to finish differential equations this week. I believe the calendar's on live, at least partially, if not completely. Got my little cheat sheet over here. Today we're doing 7.4. 7.5 and 7.9 are BC only topics, so we will not be doing those. And then we're going to wrap 7.6 into 7.7, spend a couple days on that, do 7.8 on Thursday, and have kind of our first review wrap-up session on Friday. Next week, we're going to do Unit 8. It is not tested material, but we're going to tie it back to previous units each time. And then our final 3 weeks are going to be reviewing the 2020 tested topics in addition to test taking strategies and other things we can work in. And we're all looking forward to Friday's announcement, which will give us a little more light on what the test exactly is going to look like. Our daily feature of mistakes, not going to count the weekend, not going to give us credit for 3 days, but we've got a day without a mistake. And fortunately, Virgin and I have spent enough time over the years that we have a few pictures like this, and hopefully we run out of pictures from accident-free days. So we've done our introductions. In a few minutes, we're going to do our warm-up. I'm going to hand it back over to Verge for that since she did the lesson last time. Then we'll talk about 7.4, which is reasoning using slope fields, starting to look at possible solution curves. And as usual, our guided practice is going to be wrapped into that lesson. So we'll spend about 25 minutes there. We'll wrap up. We'll let you know what's going to be in that Dropbox by 3 p.m. Eastern and what to look forward to having done for tomorrow. So Verge, here's one of the problems from Friday's assignment.
Okay, so we're going to give everybody watching live about a minute to do this. If you're watching this not live, then you can, of course, pause right now. But this was from Nancy Stevenson's handout. And this is a matching exercise where we've got 4 differential equations and 4 slope fields. And we want to try and match each one with another. So there's nothing left over. There's nothing without a match. And you've got about 45 more seconds. I do have a joke for those of us who already have a match because we did our assignment already. And the joke is this: what do baby parabolas eat?
What do baby parabolas eat, Verge?
They eat quadratic formula, of course.
Again, we are soliciting jokes, so if you want to pass along something better than that, or if you can actually find something worse, go for it.
I actually never get to tell that joke during the quadratic lesson in Algebra 1, the unit that goes on and on forever. I never get to tell that joke. So I always forget. But anyway, I'm going to have to stick this little sticky note in with my Algebra 1 stuff when I get to go back to my classroom. Okay, I'm going to go ahead. Should I grab the screen now, Mark? We've had our minute.
Go ahead.
Okay, so I'm going to see if I can do this. Oh, we need to, I cannot screen share.
So off person needs to give you co-host.
So, yes, off person needs to give me screen sharing ability.
Well, you're live and large now. Oh, but now I am.
Yep.
All right, see if you can grab it.
Okay, I got it. Okay, so this is just a paper handout of what we had. And we're trying to match the slope fields with their differential equations. So one thing I would probably notice right off the bat is this one, like number 14, dy dx equals x plus y. When you add the x and the y together, and the x and the y coordinates are opposite. So for example, -1, 1 or 2, -2, you would add them together and you would have a slope of 0. So you would have these little horizontal line segments here showing that 0 slope. So 14 which would match with A. 12, I might notice right away, dy dx equals 0.5y. This differential equation, the slopes depend only on the y value. And so as I look here, I might say to myself, okay, at a point such as 1, 0, I have a slope of 1/2. Or sorry. At 1, 0, I have a slope of 0. I'm looking at 0, 1 by accident. Sorry about that. At 0, 1, I have a slope of 1/2. So that's right there. This one matches up. On 13, this one, dy dx equals -x over y. I definitely see when I'm dividing by y, if y is equal to 0, like all along the x-axis here, I wouldn't have any slope showing because those are all undefined places. Similarly, I would have these horizontal tangents here or horizontal line segments here on the y-axis. 13 would match to D. And then 11, dy dx equals 0.5x minus 1. This one, the slopes only depend on the x value. And so when the x value is, let's see if I can do this, when the x value is 2, so for example, at 2, 3, I would have 0.5 times 2, and then minus 1, or 1 minus 1 is 0 for my slope. So I would have little horizontal line segments there, and then 11 matches with B. So that's from our lesson yesterday. And today we're going to go into 7.4, which is reasoning using slope fields. And that is sketching solution curves and making other decisions based on what we know about those slope fields. So back over to you, Mark. I'm going to stop share right now, or do you want to?
All right. All right. And this is my copy of this, and you'll have to forgive me, my printer didn't go real well. But what we want to talk about today is reasoning solutions, it says from slope fields, or carrying on into that. And so some other ways to start looking at this, and Verge, went through how we would talk about it on Friday, but also we can start thinking of, these are all rates. And so we can use our ideas of, what do the solutions look like? And something like 0.5x minus 1, what would its solution look like? -x over y, x minus y, and so forth. And so what we want to picture is, these things they're giving us pictures of solutions, right? So if we start drawing in curves, we can start trying to pretend to feel, what do these solutions possibly look like? And then what would their derivatives look like? So hopefully that's where we're going to go today. Oh, and Verge, you do have the ability to steal now, I just was told.
Okay, great. Thank you.
So when we need you to steal again, we will do that.
Okay.
So here's what the course and exam description says as far as what we're doing today. And it's solving differential equations allows us to determine functions and develop models. And we're looking specifically at solutions to differential equations, are functions or family of functions. So keep that in mind as we look at our first problem. This handout, like everything else that we've been doing, will be available in that Dropbox after the lesson. And we actually have an answer key for this one that we will put up tomorrow. We're going to make you do a little work first. All right, so the first few of these are from AP Classroom. Some are adopted from the card match that we had done that also had that Desmos activity. And of course, some of them are released exams from AP Central. And the teachers watching, welcome, and you will recognize a couple of those, I'm sure. So this says the slope field for the given differential equation, dy dx is x over y, where y cannot equal 0 and is shown below. Sketch the solution curve that passes through the point 3, -1, And you'll notice that that is highlighted right down here. And sketch the solution curve that passes through the point 1, 2. So that is right there. And you'll have to bear with me. I found out that my pen that I normally use, the battery's dead, so I have stolen my son's drawing tablet. So if you see any mistakes today, it's good because it gives me a built-in excuse. So I'm going to look through that point 1, 2 first. So what we're doing when we look at this slope field is, remember, these are all tangent lines if the function exists at those places. So all along here, we know the function exists in this solution. We're doing this one through the point 1, 2. So these give me a guideline to where the function wants to go. So I kind of want to come this way with it. And then if you think of this as a current map of like winds, if you've ever seen a map with wind currents, or off the coast, if you've seen maps of currents, if I dropped a piece of paper here, where might it go? So I'm just going to kind of stay in between these guys, use them as a channel, and sketch it through up that way. Come down, definitely going to be horizontal as we come through the y-axis. We've got some zeros there along the y-axis. And this is where you're going to have to bear with me while I'm trying to do this with the left side is always tougher for the right-handed people, and vice versa, it seems. And also this, I'm having a real, oops, that was cool. All right. One of the things I'm having with this pen that was not happening when we were practicing, is it's lagging because of the transmission, I think. I have to practice with Zoom running next time. But it is making me be more careful. So that's a continuous function. It's going through that slope field.
I was just going to ask that question, Mark. That was on the tip of my tongue. I love it.
What was it?
I was going to ask if it was continuous, because when you were drawing that, with the technology, it was making it a little harder to see the continuity of it, but definitely smooth and continuous.
Yeah, and as this pen's working, I may on the next couple go back to my camera. We'll see if it picks up on that lag at all. And then we've got this issue here all along the x-axis. What do you notice, Verge?
Seems like there's no little horizontal line segments at all.
And why is that?
And it's because y is not equal to 0. And even if we weren't told that, I see dy dx equals x divided by y, and division by 0 is not defined. So there can be nothing on the y-axis. Yeah. So when you do that little connecting with that point, it's going to have to stop at the y-axis.
I'm going to see if I can, my finger will work. Maybe
perfect.
Better to go with my finger. Yep. All right. And then as we get up to the x, we're going to have, that's where it's going to be tough.
That's a little open circle.
It should be an open hole, right?
Mm-hmm.
And there we go.
Oh, good. Yep.
Kind of a combination of my finger and the pen. So the function's going to have to stop here. There's two reasons. And again, I'm going to go back to that other slide. Our solutions have to be functions or families of functions. In this case, we're seeing two members of the family, right? These are the red and the blue here are siblings. And this is, and I guess they're brothers because there's an X and a Y here. A little shout out to my wife for the AP Bio joke. We've got this hole here because we don't know if there's a vertical tangent there. Yes, if we have points and we find a 0 denominator with a non-zero numerator, we can assume that's a vertical line slope. But this is instantaneous, and also y equals 0 is not in our functions relationship. So we put that hole there, and then we just continue the largest continuous we can. So if I wanted a domain for this, I'd have to know where that intersects, but it would only be this part to the right of that hole.
Could you say the range there is y is less than 0?
I guess since dy dx is a two variable function, for dy dx, I could say that where our solution's only good for y less than 0. I think that would be good.
I have a question, Mark.
Yes, Verge.
It's what if there was a point, like instead of them giving us 3, -1, what if they gave us like 3, 3?
Okay, so I'm gonna do my finger. So
and then we were supposed to draw the solution curve. That wouldn't be a curve, Would it?
Right. So we come back to this algebra definition of solution curve, right? Because if I come to 3, 3, and let's see, this point was at 1, 2, is that correct? This one was.
Yeah, there's your 1,
So
2.
so 3 is probably right around, this is probably about 3, 3. Oh, that other point is at 3, 1, -1, so it should be right above it. Yeah. So there's our little point right there. And you notice this, the tangent line there is a 45-degree or pi over 4 radian angle, and it shoots right to an identical slope all along that line. We still have this issue when we hit y equals 0 though, right? We still have an undefined point. So we are going to stop there. And then I'm using the touchpad this time. I'm getting to play with all kinds of technology. And it's actually going to be that ray. Yesterday when Verge was asking me about this, she asked why I didn't put arrows on my original curves. And I just said, because my calculus book doesn't put arrows on it. They continue to the edge and then they stop writing. If you put arrows on yours, you can ask your teacher how they're going to handle that in their classroom. At the AP reading, we just ignore the arrows because some people write them and some people don't. If you want the graph to stop, you draw a point at the end. Like we have a circle here, it would just be filled in if it was included.
Okay.
Right.
So a curve, basically a solution curve, really could end up to be a line segment.
Right, because the solution curve is really
or ray in this case.
a solution curve is the set of all points that makes our equation true, right? And so if we have a line y equals x, the solution curve is the set of all points that makes y equal x true, and that curve happens to be a line. And what I say in class is, lines are just straight curves, right?
Okay.
All right. So let's see. I've moved my papers around in infinite wisdom. We are just going to move along to number 2.
Mm-hmm.
Oops, I do that all the time in class. A whole bunch of kids in Denton, Texas just started laughing because I do this all the time on my Promethean board. I have to select the arrow over there before I can move things around.
Uh-huh.
All right, so here's how it looks in a multiple choice situation, the same idea. So they're not asking us to sketch the curve, but notice how this one's different than what we did last week. If we read this question, it says, the slope field for a certain differential equation is shown above. Which of the following could be a solution to the differential equation with the initial condition y of 0 equals 1? And they're using that y as a function notation, right? So that really is just saying containing the point 0, 1. We want to have this point right here. And as I was playing with this in the last couple of days, I really got disturbed by the fact that the x and y axis scales aren't the same. So we have to keep that in mind. So with Verge's warm-up and what we did on Friday, we would have been looking at derivatives down here, at dy dx's, at differential equations, and trying to decide which one would match this slope field as a solution. But this time, you notice, what does it have in front of that expression? It's
just y.
It's y equals. So these are actually they're asking, are these members of the solution family, and specifically the member of the family that would go through that point. So the way I do this, I just go through process of elimination, and I think, what does a cosine curve look like? And to me, a cosine curve should look like that, starting at 0, 1 over right about here, and then coming back the other way and doing something very periodic and similar. And this graph, it starts with the right shape, but it is flattening out before we ever reach the x-axis. So we're going to throw 1 through there. 1 minus x squared. I seem to recall hearing a joke about these types of equations recently.
Yep, my Algebra 1 students could totally tell you what that looks like.
That is indeed a parabola, and it should be getting steeper the farther down we go, especially as it hits these intercepts here. So we're going to throw b out. C, our exponential function, which I imagine its derivative looks very similar to that.
Yep.
And so our exponential is going to look like that. It has the horizontal asymptote at 0 on the left. That makes me happy. But obviously the right side is not going to work out. D, and D is the reason the scale bothered me. Because Verge, what do you notice about D?
Well, D is the top half of a circle. If you
Yeah,
have x squared plus y squared equals 1 and solve it for y, yeah.
Yeah, if I went through and actually solved this thing and tried to get, well, not solving it, it is solved for y right now. I'd end up with an expression that looks really similar to x squared plus y squared equals 1. Now, this principal square root is what, Verge, of course, is absolutely correct. It's the top half of the semicircle because they chose the positive square root here. And this is the one that when I tried to draw it on here, I realized how bad the scales were.
Mm-hmm.
Because if I go from 1 to -1 and 1 to 1, it actually looks very similar to our parabola. It doesn't look like a semicircle. So I would prefer it to be more semicircle-ish, which this apparently is not that. This is more of a tent. But as best I can, it still obviously violates or goes against the slope field down there. So we're left with E as our answer. Perhaps we can figure out exactly why. And this one, I'm going to actually try to use the pen. I'll probably regret this, but if yeah, I already do. Okay. Sorry about that, guys. That was something I did not realize until about 12:50 that this was doing that. But if I look at the limit, and I'm not going to be able to do this with a mouse pad, I'm sorry. But if I look at the limit of this, as x goes to positive and negative infinity, we have that polynomial on the bottom that's second degree, this monomial on top of degree 0, and that limit is going to be 0. So we're going to get that horizontal asymptote on both sides at 0 that we expect at y equals 0. And it's going to start through 0, 1 and go through. And I know Verge, when she did this, when we talked about this from earlier, she'd also verified 0, 1 worked in all these right off the bat. And unfortunately, they all did. So that didn't help us eliminate anything. So, and I'll just go ahead and let the people who want text me, but this guy has a special name, but I'm not going to throw it out there specifically because I don't want anyone worrying about stuff that they have to not know. Any questions you have on this, Verge? Anything to add?
No, looks great.
Awesome.
I think we're saying the answer is E. Mark didn't circle it, but
oh, I'm sorry. Yes,
but he didn't knock it out either, and he was talking about saying yes, it's definitely E.
Yeah,
by process of elimination.
Definitely E. All right, so I'm gonna go to my next slide. And oh no, words. This is when a lot of my students are like, why do I have to put so many words around it? But we're going to get through those words. We're going to read through this. So we have the number of frogs living in a pond at time t, measured in weeks, is modeled by the function y equals big F of t that satisfies the differential equation dy dt is equal to 1/2500th of y times the difference of 1010 in y. The number of frogs in the pond at time t equals 0 is f of 0 equals b, where b is a positive constant. So we don't know how many frogs we're starting with other than it's a positive number, which if you're going to have a population, that's a good place to start. A slope field for the given differential equation is shown in the figure below. Sketch the solution curve that passes through the point 0, 250, and sketch the solution curve that passes through the point 0, 1500. And I do want to take a moment and point out, and one of the previous problems had this as well. You'll notice that they're two different solution curves. It's not sketch a solution curve for both. So if anyone's concerned when we go back, and I did it in 3 colors to kind of emphasize that, oh, I can't go back because of the drawing.
No, but this, you know what, Mark, you're saying exactly what was in my mind. And that is when we draw the first one, that is a solution curve, its
right.
own standalone.
It's only the one through that point, right?
Yes. And then we're saving our resources here and using the same graph to draw a separate solution curve.
Correct. So yes, it's they are not both solutions at the same time because they would fail the vertical line test very hard. Okay, so let's see if I can stay through these. Oh no, I don't like the ending of that. So what I'm trying to do when I draw these, for those of you that are obviously you're watching and can't see what I'm doing with my finger. I'm trying to stay in between lines if I do, or if I get a line, I try to run parallel to it. So I'm kind of, and then this thing gets flat really fast, and it's supposed to be asymptotic. You'll have to forgive my finger there. And they did not restrict this, so if you carried it to the left, I think it would be okay, but realize that we have a starting point of 250, so I'm going to start my graph there. All right, and you'll notice it gets closer and closer to that 1,000 without ever quite getting. Actually, that line is actually, I think, a little above the 1,000, but that's okay. They gave us the solution. They
It's
gave us the
actually,
slope field.
yeah, you can tell by the equation that it's
Yeah,
actually
in
1,010.
1,010, that would equal 0 again, wouldn't
Yeah.
it? Yep. And now we're going to look at the 0, 1,500. So I'm going to put my point there. So we're starting off above now. And kind of come through and see how asymptotic I can get. So no matter which side we start on, we start approaching that 1,010. And again, you don't have to do all this, but if you look at the equation, when you plug numbers in that are larger than 1,010, you will notice you're getting negative slopes back. And as soon as you put in a number less than 1,010, you're going to get positive slopes back. So that is consistent, which is good. I always like it when math works. So, all right. And I'm going to erase it and change the arrow so I don't draw two little finger lines on the board like I did before.
Oh, you're learning so fast, Mark. You're so smart.
Yes. All right. I am going to turn my camera on for a second, and I want to do this because I want to kind of give you guys a guide of how do I do this at home. And if you're stuck like me with a mediocre printer, I actually had issues that my printer didn't want to print these. So I'm going to actually do the last problem, and I know you can't see it, but if I was doing this, I don't expect you guys to draw the hope slope field. I wouldn't expect my students to. So, and can you see that okay?
Yep.
All right.
It's kind of,
it's blurry. Yeah,
it's
there
focusing.
Okay, because I can't see it when I'm looking at the other thing. And I would just do this and say, all right, there's my 1,000, usually with 3 zeros, 500. And it looks like they went out to 60, cut it in half, call it 30. And then just kind of do the sketch without having to put the slope field in, or if you want to put a couple of the slope fields in, be like, okay, it's going up. But you can still draw this without having the slope field in front of you and just know it's that shape. And then 500 more. And so you can draw these without having the slope field on a piece of paper. Obviously, it's easier with the paper, but we're adaptive people. And if nothing else in these times, we have found out we're adaptive people. So are you seeing my screen again? Okay.
Yep.
So we're going to give you a little bit of time to do number 4 here. As you start, I'm going to read the directions. It says for the given differential equation, sketch the solution curve that passes through the point -4, 4. And you can see that one highlighted here in the second quadrant. Sketch the solution curve that passes through the point 6, 2. That's this one over here in the first quadrant. And sketch the solution curve that passes through the point -2, -3. And while we're doing this, I guess Verge is should be working on hers on off screen. I'll give you a minute or so since this is a lot to do, I know. So take a moment to take it in. The dy dx is x minus y. And you can pause this and come back, or I will tell a joke since Verge told a joke. This one was sent to me by a teacher. We've been told to avoid names on here, so I'm sorry, you're just gonna have to know that you're getting credit unless we use one of your documents. But my house has been chilly. I'm in Texas, but I'm in North Texas. Our weather is up and down. We hit the 90s this week. It was in the 40s a couple nights ago, maybe even last night. But I found that if I do my math in the corner, I feel a little warmer because it's always 90 degrees there.
Yeah.
Yeah, it wasn't. I
And you
know.
thought mine was bad?
Oh, yeah. Well, mine's bad because, I mean, really, who uses degrees? All right.
Yeah, oh, that is so true. You're having a problem with your calculator. It's probably because you left it in degree mode from physics.
Yes.
Okay, so here's mine, Mark. How do they look?
Well, let's see. You're hitting the point, and that's very important. How close
Uh-huh.
enough? People are always like, how close enough is close enough to the point? Hitting the point is close enough. You came through. We got this horizontal, and then what appears to be this vertical. And you know you don't hit that asymptote, or at least you should suspect you don't hit that asymptote, because if you do get to it, you're going to stay on it, and that's probably very unlikely. So, plus we can see where it equals 0. See 0.62. That looks good. Maybe a little steep there at the end, but who am I to talk after the digital stuff I've been putting up? And then at -2, -3, and I notice your point doesn't stop at either of these zeros here. It keeps passing right through, unlike mine from that earlier problem.
Yeah,
Why didn't you
so
stop?
why didn't I stop? Well, this differential equation here doesn't have any places where it's not defined. In other words, I'm not dividing by X or dividing by Y. So I think I can just continue to subtract Y from X for the entirety of the coordinate plane, basically.
That's
So I
right.
just kept on going.
Yeah, we stop if we hit an undefined point, and you did
Mhm.
not.
Yeah. Yeah. I did it right.
Yay, Verge!
Until somebody tells me later I didn't do
Right, yes,
it.
we're really hoping to get a 2 up there on that screen tomorrow. Oh, if we ever hit non-prime again after 1, that'd be so nice. Okay, so let's see. What are we gonna do next? Oh, that's the end of this page. My
Number
digital book here. Okay, these, you're gonna see a couple go by right here, and I believe we're gonna do number 6. Now, I'm gonna blow this up in a second. You will notice that it's the same 3 points on every graph. So -4, 4 is getting a solution curve, 6, 2 is getting its own solution curve, and -2, -3. So we're getting 3 members of the family. And I'm gonna blow that up. And should we give people a moment to do this one, or do you just want to go ahead and
No,
do
because
it,
I want to get
Verge?
to that AP one at the end. Remember, we're going to do the
Okay.
AP. So I think you can
So,
just do this one.
all right. What I really want to use is my geometry cheating skills, but there's a figure drawing device over here. So I'm looking at a point at -4, 4. So I'm thinking it's going to look something like this. Does that purple show up, or is that a little light?
To me, it does. I can see it. Yep.
I'm actually going to still choose the darker purple. And again, we're not supposed to mention names, but if our chief reader ever happens to tune in,
Oh,
she
yeah.
will appreciate that. All right,
Mhm.
I'm gonna see if I can do this with the mouse. It's gonna be awful no matter what.
I think if you're watching at home, getting entertained by Mark and his novice drawing abilities in this format, you hopefully were looking at this kind of a bullseye type slope field, and hopefully thinking to yourself, it reminded you of circles, and maybe we would be drawing a bunch of circles. But Mark is drawing only semicircles here
And missing the endpoints as
and
well.
not including the endpoints. And if you look back at that differential equation,
Ooh, I'm getting braver
you can
and
see
and
why.
paying for it.
Anytime we have 0 in the denominator of that differential equation, it's going to yield something that's not defined. And so we cannot include that in our sketch.
Right, and I know there's going to be a lot of people who are working these backwards, and or you recognize derivatives, and the derivative of a circle is that dy dx is -x over y. But the problem is we don't know where this came from. If this is just a rate formula someone found, if it is a derivative of a relationship, it would have to be an implicit relationship in that case, or a piecewise relationship. And so we just can't say that y = 0 is there, because remember, these are the solutions that we're drawing. And the solution inherits the domain's restrictions of the original problem. And since this original problem doesn't include y equals 0, we can't know that the solutions can include y equals 0.
Mhm.
So, all right, how's that?
Looks great. And I think, again, we could actually, for example, for that blue semicircle, we could discuss the domain and the range if we would carefully calculate the radius. That would take,
Right.
it wouldn't be hard to do, but we're not going to
It
do it
was really
right
easy this morning. I just asked Alexa to do it for me, and she gave
now.
it to like 5 decimal places.
Really?
I just asked her what is that point? Is that one, is that the -2,
That's
-3?
-2,
Yeah,
-3.
I asked her what the square root of 13 was, and she rattled it off to like 4 or 5 decimal places, and I guarantee Siri can do it too. So
Yeah, so I guess the range would be 0 to square root of 13, including the
right.
square root of 13, but not the 0, and then yeah, we could totally do that. All right, let's do our last example, though.
All right. So, oh, and I'm doing my same. Okay. So this is from 2014 AB6. As you can tell, we cleverly camouflaged the source by putting it in the upper left corner. And it is, consider the differential equation dy dx equals 3 minus y times cosine of x. Let y equals f of x be the particular solution to the differential equation with the initial condition that f of 0 equals 1, and the function f is defined for all real numbers. And you notice they gave us the initial condition in the stem, and a lot of free response questions, they'll take advantage of the fact, and I'm going to throw it up here one more time, that solutions, and this, I'm looking at this bottom right, is families of functions. And so sometimes on FRQs, which is, sorry, abbreviations for free response questions, they might change the initial condition throughout the problem. Like the potato problem did not do that, but there's been some others that do. But they gave it to us here at the beginning. So I'm going to go ahead, and I've got it. The only ones they labeled on here are the 3. So 0, 1 is right about there. So look at those tick marks, figure out where it is. And part A says sketch the solution curve through the point 0, 1. So let's see how good of a job I can do. And Verge, do you want to talk about what happened when real students had to do this?
Well, I don't think I read this question back in 2014, but I remember you saying that they plotted the point in the wrong spot.
A lot of kids missed that 0, 1, which I almost did, and I was just making the point really big.
I could imagine a lot of students did not dip into the third quadrant like they should.
And I think I actually dipped less than it should have. I think I'm actually going
Mhm.
across some of them right there.
I think
Do
a lot of
realize if this shows up on an AP test, they're very forgiving. You don't have a protractor, you don't have a ruler. I changed colors, which is really weird. So you don't want to spend 15 minutes on this, but you do want to make sure you're fairly close to what's going on. All right, what do you think of that, Verge?
looks great.
Other
And
than that,
also it said the function f is defined for all real numbers. I mean, that's also a clue that you should kind of stretch out along the entire coordinate plane.
good. All right, and then we're going to get some embedded review here. We've got about 5 minutes left. It says down here in part B, it says write an equation for the line tangent to the solution curve in part A at the point 0, 1, which is our same point. And then we're going to use that equation to approximate f of 0.2. Now, depending on how long you have been out of school, when you guys started the AB curriculum, I know some people start in January, but some people may not have found a tangent line in a while. So Verge, remind me again, what do I need to find the equation of a line?
Well, whether you're in Algebra 1 or AP Calculus, you need two things to write the equation of a line, in my opinion anyway. Ideally, you have the slope and you have a point. If you have those two things, you can write the equation of the line. So for calculus, the slope is the same as the derivative. So we actually have a recipe here, a formula for the derivative. We're told that dy dx is equal to this product of 3 minus y and cosine x. So if all you have to do really is fill in.
Sorry. I'm getting way too picky, but this is horrible. That's all right. You guys can go online and talk about it. I'm still trying to find if you guys are talking about us on Discord or not. All right. All right, so at 0, 1, I'm going to have 3 minus 1 times
Wow, that is
cosine of
bad,
0.
Mark.
Oh, shush.
What in the world?
All right, I could yell
That's
for my son to
2.
bring me a
That's
better
2.
stylus. Ah. All right, I am going to try one more time with my tablet. Let's see if it's gotten any better. But no promises. Oh, no, it's not even responding now. Okay. How did you guys fill 45 minutes every day? A lot of technological errors. Yeah, see, this is horrible. Okay, I am going to
Steal
just,
it
we're
if you
just,
want. Do you want me to steal it?
yeah, why don't you go ahead and steal
Okay.
it? That'd be awesome. 3 minus 1 is 2, and cosine of 0 is 1. So I'm going to go with 2 for my slope, if that's okay.
Yeah.
It's,
Okay, so this is our problem. So what Mark said was at, and the notation. So the notation here, dy dx at 0, 1 is going to be 3 minus the y value of 1 times cosine of 0. So we have 2 times 1, which ends up being 2. That's our slope. And then what was our point?
the point 0, 1.
Okay. And then, my AP calculus students a long time ago said goodbye to y equals mx plus b in favor of point slope form. It took some of them longer than others to completely jettison y equals mx plus b. But this is much better, in my opinion. How does
Many
that look,
people's
Mark?
opinions. Yes.
Y minus 1 equals 2 times x minus 0 is my tangent line. And then I'm going to approximate the y value on the f function when x is 0.2. So I can say y minus 1 equals 2 times 0.2 minus 0. 0.2 minus 0 is 0.2. 2 times 0.2 is 0.4. And then I'm going to add the 1 to both sides. So I get y is 1.4. So those are kind of what I was being asked to do, write the equation of the tangent line and then use it to make the approximation. It's okay if you have equals here. The implication is that 1.4 is the approximation for f of 0.2.
And I'm just going to add one thing. I'm going to steal this back, I think, for the last time today. This is the way I have point slope memorized.
Oh, yeah.
And this is really cool because for those of you that have already played with accumulation models and things like that, this is your old y plus the change times the width. And it shows up again and again. BC kids, if you're watching this later or as review, this is actually called the Taylor form of the line. That's all I'll say about BC. So everyone else come back. But that is actually a first order Taylor or first degree Taylor polynomial as well.
Very nice.
All right. So I'm gonna steal from myself now. And just a reminder to everyone out there as we're finishing up, if you know anyone that does not have access to the internet, or you're not happy with, you're trying to watch this on your phone and do all the math on your phone, please reach out to CB, it's CB for College Board, cb.org/tech. It takes you directly to a survey and you can fill out what your role is, whether you're a student or a teacher, and if you're reaching out for yourself or someone else. And we're trying to get connectivity and tools to everyone that needs them. So please take advantage of that. Thanks for watching.
We'll be
go ahead,
live
Virg.
again. Yeah, we'll be live again tomorrow. We're live 5 days in a row this week. So hopefully you can watch us live or after the fact.
And there are 2 activities in the Dropbox today, or they will be in about 15 minutes. The problems you saw us working today, and we did not work all of those. There's a practice AP problem on there from 2018, as well as number 5 and 7. So you can look at those on your own. And there's a 4 corners activity, which kind of wraps up unit 7. And you can do the first 3, and the 4th box is a preview of the next couple days, if you want to go ahead and take a look at that.
Right, because we're really going to start slinging some separable differential equations tomorrow.
And technology won't be as much of a problem because we're done drawing pictures for a while at least.
Yeah.
All right. Thank you, everyone.